So we now know that the derivative of f of x is given by f prime of x, and it's the limit as h approaches 0 of f evaluated at x plus h. From that we subtract f evaluated at x, divide by h, and take the limit as h approaches 0 of that entire quantity. And knowing this, we could theoretically compute derivatives using this definition every time. But the algebra gets really awful very quickly. Fortunately, there's some simple rules we can use to find derivatives, and we'll see what these rules are and how they're helpful to us over the next few videos. But before I get to the rules, I have to mention that some of them are predicated on functions being differentiable. What does that mean? Well, we'll say that a function is differentiable, just abbreviate that diffable, if this limit exists. So if limit as h approaches 0 of f of x plus h minus f of x over h exists. And that's actually quite a deep statement, but we'll get to more on this later. First rule is that for any rational number n, the derivative of x to the n with respect to x is n times x raised to the n minus 1 power. So an example of this would be the derivative of x to the 4/3. That'll be 4/3 times x to the 1/3. And how should we interpret this? Well, we should interpret it like so. If you want to find the instantaneous slope of the function x to the 4/3 at a given value of x, you're going to have to plug that value of x into the function 4/3 times x to the 1/3. So let's say we wanted to find the instantaneous slope of x to the 4/3 at x equal to 1. We'll plug x equal to 1 into the right side here, which is the derivative, and we'll get, well, 1 to the 1/3 is cube root of 1, that's 1. 4/3 times 1 is 1. So 4/3 times 1 is 4/3. So 4/3 is the instantaneous rate of change of x to the 4/3 at x equals 1. The next rule is that for any differentiable function f of x and some constant c, the derivative of this constant times that function is the constant times the derivative of the function. So let's say you want to find the derivative with respect to x of the square root of 5x. You'd see, well, that's going to be the derivative with respect to x of the square root of 5 times the square root of x. And all this is inside of that derivative operator. And this property tells us that we can pull this square root of 5 outside of the derivative and evaluate this as the square root of 5 times the derivative with respect to x of the square root of x. And that's just going to be the square root of 5 times the derivative with respect to x of x to the 1/2. And we now know that this is going to be 1/2 times x to the minus 1/2, because that's of this form here, n x to the n minus 1. So we'll just have square root of 5 times 1/2 times x to the minus 1/2. Or alternatively, we could write this as the square root of 5 divided by 2 times the square root of x. So properties 1 and 2 give us enough information to find the derivative of a constant function. So some number c. And remember, property 1 just says that for any rational number n x to the n, the derivative of x to the n is n times x to the n minus 1. The second property says the derivative of a constant times a differentiable function of x is that constant times the derivative with respect to x of that function. So how can we use that in finding the derivative of a constant function? Well, before we do that, Just ask yourself, what does the constant function look like? Well, if we sketch a set of axes here, this is the x-axis, this is the y-axis, and let's say have y equal some constant. And we can see here that the derivative, which is basically the instantaneous slope, is not really going to be changing regardless of what x is. In fact, it's going to be 0 everywhere. So we'd expect that the derivative of a constant function is going to be 0. But let's use some of those rules to verify that. So the derivative with respect to x of some constant c is going to be the same thing as c times it's going to be the same thing as the derivative with respect to x of c times x to the 0 power. And we know we can pull out the constant, so that's going to be c times the derivative with respect to x of x to the 0 power. It's going to be c times 0 times x to the minus 1. Well, we have 1 0 factor in this expression. Anything multiplied by 0 is going to give you 0 as a result. So the derivative of a constant is indeed 0, as we expect. This next property says that for differentiable functions f of x and g of x, the derivative of a sum f of x plus g of x is really the sum of the derivatives. And the derivative of the difference f of x minus g of x can be evaluated as the difference of the derivatives f of x and g of x. So let's say, for example, we wanted to find the derivative of x cubed minus 8x. Well, we can evaluate this as the difference of the derivatives of x cubed and 8x with respect to x. So we can evaluate the derivative of this difference as the difference of these two derivatives. So using the power rule, the scalar multiple rule, and the sum rule, we can actually evaluate the slope, the derivative of a generic line with respect to x. But to review, the sum rule, the power rule is this rule here. Derivative of x to the nth power is n times x to the n minus first power. Scalar multiple rule is just that. The derivative of constant times a differentiable function of x is that constant times the derivative of that function with respect to x. And the sum rule just says that you can evaluate the derivative of a sum as the sum of derivatives. So using all of that, we'd like to find the derivative with respect to x of a generic line, the equation mx plus b. Well, what would you expect its derivative to be? Well, let's say we have a typical line here with y-intercept b and slope m. Well, the derivative is the instantaneous slope, or the slope at any given point x. And for a line, we'd expect the slope to be fixed. We'd expect it to be a fixed value m. So we'd expect the derivative to be m regardless of what x is. But let's verify that. So this derivative of mx plus b is the derivative with respect to x of m times x plus the derivative with respect to x of b. But we know that the derivative of a constant is 0, so this is 0. And we know here we have a scalar multiple m times x, so this is just going to be m times the derivative with respect to x of x. And that's going to be m times, well, this is x to the 1, right? Derivative with respect to x of x to the first power. And that's just what? See, are we running out of space here? Let's kind of ignore this. So this is m times 1 times x to the 0th power, right? So that is just m times 1 times 1, and it's m. So as we would expect, we do get a constant value of m for the derivative, a line with slope m. So now let's see if we can put all these rules together to find the derivative of yet another function, a slightly more complicated function this time. So let's say f of x equals the cube root of x plus 5x squared plus 6x plus 7. Well, what is f prime of x? And note for reference, I've just put up the 5 formulas we've stated in this lecture so far. Okay, so this is going to be the derivative with respect to x of this entire sum. Well, that's just the sum of each of these derivatives, right? So this is going to be the derivative with respect to x of, well, cube root of x is x to the 1/3. Plus, well, the derivative with respect to x of, I guess we'll say the derivative with respect to x of 5x squared. And then what? Plus the derivative with respect to x of 6x. Plus the derivative with respect to x of 7. So this derivative here is just going to be 1/3 times x to the minus 2/3. This derivative here is going to be 5 times the derivative with respect to x of x squared. This derivative here is just going to be 6, right? This is of the form mx plus b, so the derivative just m. And this here is a derivative of a constant. This is going to be 0. Okay, so we have 1/3 x to the minus 2/3. I can just write that as 1/3 x to the 2/3. 5 times the derivative of x squared. Well, the derivative of x squared is going to be 2 times x to the 1, or 2x, right? So 5 times 2x is 10x plus 6 plus 0. And we're almost at our answer. So 1/3x to the 2/3 plus 10x plus 6.